Fermi theory of beta decay. In 1934, Fermi developed a successful theory of beta decay based on Pauli's neutrino hypothesis. The theory is based on the following assumptions. They are: the radioactive nuclei emits electrons and positrons. They do not pre-exist inside the nucleus. They are formed when either a neutron transfers into a proton or a proton transfers into a neutron. Along with the electron, an antineutrino, and with the positron, a neutrino is also emitted. Beta decay obeys the law of conservation of energy. The available energy is shared among the electron and the neutrino. The rest mass of neutrino is 0. Electron-neutrino field is weak. That means a weak interaction is taking place there. Hence, the system is ideal for time-dependent perturbation theory. So, with the application of this time-dependent perturbation theory, Fermi is trying to solve the beta decay. Fermi used the result of Dirac's time-dependent perturbation theory, according to which the rate of transition from an initial state, an initial state I to a final state F is given by Fermi's golden rule as lambda equal to 2 pi by h cross Vfi. That means you are considering the magnitude of Vfi square into rho Ef. So this lambda is the rate of transition. Vfi is the matrix element of interaction causing the transition, and rho of Ef is the density of final states. That Ef represents the energy. The matrix element Vfi is the integral of the interaction V between the initial and final states of the system, and you can write Vfi as integral psi f star V psi I. This is the normal way you are taking the thing in quantum mechanics. Always you are taking the integral psi star psi, that is a method you are taking. So final state psi f star, and V is the interaction acting on it. So psi I and dV is the volume element. And now rho Ef can be written as dN by dEf. The number dN of final states in the energy interval Ef. That is the number density. That means particular numbers in a particular energy interval Ef. According to Fermi, the beta emitting nucleus makes a transition such that the final stage consists of the product nucleus, that you are normally calling as the daughter nucleus, plus the electron and the neutrino. The initial state is the parent nucleus. So we have already written the expression as Vfi equal to integral psi f star v psi I dv. That we are rewriting as, first you are putting a g, then integral, and in place of that psi f star, we are now writing as psi f star, psi e star, phi e star and phi nu star, and in place of that v, you are writing as ox psi I dv. There you can, psi I star is the final nuclear wave function. It is only the final stage of the nucleus, and phi e star is the wave function of electron, and phi nu star is the wave function of the neutrino. And when these three are together, it is the final state of the system. It is the quantity in the square bracket represents the entire final system after decay. That is this quantity. This represents the final state of the system. And this is the initial stage, only one nucleus. G is a constant whose value determines the strength of the interaction. It is like your coupling constant or G factor. And the interaction V can be replaced by the interaction operator OX. Initially we have written as V, and now we are rewriting it as OX, where the X subscript gives the form of the operator O. And this operator can be either scalar, vector, axial vector, pseudo-scalar or antisymmetric tensor. And which of these form is correct for beta decay can be revealed only through experiments that study the symmetries and the spatial properties of the decay products. It took more than 20 years for the correct form to be detected, and between this so many false conclusions or mistaken conclusions were already. The density of states determines the shape of the beta energy spectrum. Density of state means it is the number of electrons in a particular energy stage. So here you can see that here, say example here, you have some electrons with a particular energy. So this is the number in that energy. So this shape is determined by the value of that density of states. So if we can measure that density of states, or if you can have an expression for that density of states, you can get a clear idea, or you can have an idea regarding the beta decay. And that actually we are doing in this derivation, which was done by Fermi. So in order to calculate the density of states, we need to know the number of final states accessible to the decay products. In the decay, you have an initial stage and also a final stage. So a number of final states are getting. That is why you are getting a wide range for that spectrum. So we must know the number of final state accessible. Not all states may be accessible to the initial stage. So that interaction is determining actually what is the final state the electron has to reach. Okay. So in the decay, consider we have an electron or positron. emitted with momentum p and a neutrino or antineutrino with momentum q. And we are now interested only in the shape of the energy spectrum, and thus the directions of p and q are of no interest. Actually, you can see that there is a particular direction for the emission of electron, another direction for antineutrino or neutrino, whatever may be. We are not now interested in that case, but we are just considering as for explaining the shape of the energy spectrum we have already obtained. If by developing a theory, if we will be able to describe the shape of that spectrum with our developed theory, our theory is a successful theory, and that actually we are doing. So, if we imagine a coordinate system whose axes are labeled, that means you are considering as px, py and pz, then the locus of the points representing a specific value of p, actually this p you have to consider as a vector, so we are now taking it as only magnitude. P is equal to px square plus py square plus p square z square whole raised to half, a known expression to us. So, a particular momentum p can have three components, px, py and pz. So, with this, in that momentum space, for a specific value of p, you can have a sphere of radius p. And this type of calculation we are normally doing in statistical mechanics. So, the locus of points representing momenta in the range dp at p is a spherical shell of radius p and thickness dp having volume 4 pi p square dp. So, with the value p that you can assume or you can visualize, you have a momentum p. So, in that momentum space, you have a sphere with the radius p, and you have we will be always considering like that in the momentum range p to p plus dp. So, p means p plus dp is slightly greater than that. So, you have, and with that radius p plus dp, you can consider another sphere. So, between the spheres with these concentric spheres with radius p and p plus dp, you will be getting a small shell with the thickness dp. So, the volume of that shell will be 4 pi p square, that is a 4 pi p square dp, that is a first sphere into thickness. If the electron is confined to a box of volume V, then the number of fine electron states dne corresponding to momenta in the range p to p plus dp is, this dne is the number of electrons which are in the momentum range p to p plus dp. You are writing it as this 4 pi p square dp, that is the volume of the spherical shell in the momentum considerations. And if V is the volume, you have to multiply it with that volume V. So, this is the actual thing you will be getting. And we are dividing it with h cube. And the next slide, we will be explaining the use of that term h cube. Actually, you know that in a 6-dimensional phase space, that means with the momenta and coordinates, you will be getting a 6-dimensional space where volume of a unit element is HQ. So this has the dimension of volume. So this is a number actually, and this is the dimension of volume. So if you are dividing it with another volume, this number will be purely this will be a pure number and no dimension of momentum. No dimension of volume. That is why you are using such an equation. The factor h cube is included to make the result a dimensionless pure number. And similarly, the number of neutrino states in the range q to q plus dq you can write as, where that dnu is the number. Last we have for electron we have written as dne. Here it is dne nu equal to 4 pi q square dqv by hq. The number of final states which has simultaneously an electron and a neutrino with the proper momenta is, you are writing as d squared n, which you can take as the product of dne and dnu, and they were 4 pi by h cube v square p square dp for electron and q square dq for neutrino. So combining them it will be 4 pi the whole square v square p square dp q square dq by h raised to 6. And now the electron and neutrino wave functions have the usual free particle form normalized within the volume V. We have started with the volume V, and if the wave functions are free particle, that means you can now write the wave function as, this is the normal, the famous wave equation used by us. And for normalization, this 1 by root V you are commonly using. So 1 by root V e raised to I p dot r by h cross. This is for the wave function of electron, and similarly by replacing the p with the q, you will be getting the wave function for neutron. And for an electron with 1 mega electron volt kinetic energy, this p you can calculate as 1 by 1.4 mega electron volt by c, and the number p by h cross as 0.007. It is the femtometer. That means that p by h cross has the dimension of r. It is a very small value. Thus, over the nuclear volume PR, that PR over the nuclear volume means this R is also very small. This PR will be much less than 1, and we can expand the exponentials keeping only the first term. That means you are now expanding this e raised to I p dot r by h cross as the form e raised to x with 1 plus x square by 2 factorial, your exponential, your binomial expansion. And this term is very small. That is why you can neglect this, and this is approximately equal to 1, and this is also approximately equal to 1. So this approximation is usually known as the allowed approximation. And but with this allowed approximations, you are getting the electron wave function phi e of r as 1 by root v, and that of that antineutrino also as 1 by root v. The partial decay rate for electrons and neutrinos with the proper momenta is. This was the equation we have initially written. Lambda is equal to 2 pi by h cross Vf phi square rho Ef. And now we can replace this rho Ef with the dN by dEf, which we have already mentioned. is the density of states, which can be written like this. And this decay rate, since it is small, you can replace that lambda with d lambda. If we have to take some integration, etc., this d lambda will be useful for us. That will be we will be taking it as d lambda. So this is the expression. Now, what now we will do is, we have an expression for dn and we have an expression for vfi. By substituting them in this equation, we can simplify the equation to get the decay rate. This was also already written. Vfi is equal to g into integral psi f star psi e star psi nu star ox psi I dv. Once again, Vfi is equal to g into integral. In a square bracket, you are writing as psi f star phi e star phi nu star ox psi I dv. Now you can substitute for this phi e star and phi nu star with 1 by root v, 1 by root v. So your d lambda now becomes 2 pi by h cross g into integral psi f star 1 by root v ox psi I dv, that's whole square, dn by def. And now we are substituting for dn. dn is 4 pi square v square p square dq q square dq divided by h raised to 6. So this is in place of dn and this is def. And here only v, not v square. Psi f star 1 by v, that I will correct. So this v, you have a square here. So this v square and this v square cancel each other. So you will be getting the equation for d lambda as 2 pi by h cross g squared mfi square 4 pi square p square dp q square dq h raised to 6 by def. Now we have a new term, mfi square. What is mfi square? This is cancelled. So this term, that means integral psi I star, this ox, and psi f star ox psi I dv is the nuclear matrix element that you are writing as mfi.